Hello, my name is Samantha Winchell, and I'm a student at FRC. Today, I will be showing you how to do hypothesis testing. Before we review how to do the various methods of hypothesis testing, we need to understand some of the definitions. There are a lot of definitions, but it is imperative that you have a basic understanding before you can apply what you know. A hypothesis test is a procedure for testing a claim about a property of a population. The null hypothesis, denoted by H sub 0, is a statement that the value of a population parameter, such as proportion, mean, or standard deviation, is equal to some claimed value. The alternative hypothesis, denoted by H sub 1, is a statement that the parameter has a value somewhat differs from the null hypothesis. The symbolic form of the alternative hypothesis must be one of these symbols: less than, greater than, or not equal to. The significance level alpha for a hypothesis test is the probability value used as the cutoff for determining when the sample evidence contains significant evidence against the null hypothesis. The significance level alpha is the probability of mistakenly rejecting the null hypothesis when it is true. The test statistic is a value used in making a decision about the null hypothesis. It is found by converting the sample statistic, such as p hat, x bar, or s, to a score such as z, t, or chi-squared, with the assumption that the null hypothesis is true. The critical region, or rejection region, is the area corresponding to all values of the test statistic that cause us to reject the null hypothesis. The p-value is the probability of getting a value of the test statistic that is at least as extreme as the test statistic obtained from the sample data, assuming that the null hypothesis is true. A critical value, or values, separates the critical region, where you reject the null hypothesis, from the values of the test statistic that do not lead to the rejection of the null hypothesis. The power of a hypothesis is the probability 1 minus b of rejecting a false null hypothesis. The value of the power is computed by using a particular significance level alpha and a particular value of the population parameter that is an alternative to the value assumed true in a null hypothesis. A type 1 error is the mistake of rejecting the null hypothesis when it is actually true. The symbol alpha is used to represent the probability of a type 1 error. A type 2 error is the mistake of failing to reject the null hypothesis when it is actually false. The symbol beta is used to represent the probability of a type 2 error. In order to properly test a hypothesis, you have to use a formula that relates to the situation in your problem, and certain conditions must be present in order to use a particular formula. A test statistic for a proportion must have a p hat, which is equal to the sample proportion, and is found by doing x divided by n, x being the number of successes in the sample and n being the sample size. P equals the population proportion, Q is 1 minus P, and the formula would be Z equals P hat minus P divided by the square root of P times Q divided by N. A test statistic for the mean sigma known is X bar equals sample mean, mu equals population mean, sigma equals population standard deviation, and N equals sample size. So the formula would be Z equals X bar minus mu divided by sigma divided by the square root of n. The test statistic for mean sigma not known is really similar. It has X bar as the sample mean, mu as the population, S as the sample standard deviation, and n as the sample size. So the test statistic would be T equals X bar minus mu divided by S divided by the square root of n. The test statistic for standard deviation is n equals sample size, S equals sample standard deviation, and sigma equals population standard deviation. And that would be x squared equals in parentheses n minus 1, so that means you do that first, then you times that by s squared, and then divide it by sigma squared. The population proportion for normal approximation method have the requirements of the sample observations are a simple random sample. The conditions for a binomial distribution are satisfied, which are there's a fixed number of trials, the trials are independent, and each trial has two categories, success or failure. And the probability of success remains the same in all trials. The conditions NP greater than or equal to 5 and NQ greater than or equal to 5 are both satisfied. So the binomial distribution of sample proportions can be approximated by a normal distribution with mu equals NP and sigma equals square root of n times p times q. So the test statistic would be z equals p hat minus p divided by the square root of p times q divided by n. Population mean with sigma known, the requirements are the sample is a simple random sample, and the population is normally distributed. And a test statistic would be z equals x bar minus mu divided by sigma divided by the square root of n. The population mean with sigma not known has the requirements of the sample is a simple random sample. Either or both of these conditions are satisfied. The population is normally distributed, or n is greater than 30. The test statistic would be t equals x bar minus mu divided by s divided by the square root of n. And finally, the population standard deviation or variance has the requirements of a sample is a simple random sample, the population has a normal distribution. The test statistic would be x squared equals parentheses n minus 1 and parentheses s squared divided by sigma squared. Now it is time to review the steps we use when going through hypothesis testing. Let's use an example to walk through as we review the steps. In a study of the accuracy of online orders, one company has 48 orders that are not accurate among 495 orders studied. Use a 0.05 significance level to test the claim that the rate of inaccurate orders is equal to 10%. Does the accuracy rate appear to be acceptable? Step 1 would be to identify the claim and express it in symbolic form. You should note that the hypothesis is a claim or statement about a property of a population. For our example, the claim that 10% of online orders are inaccurate. The symbolic form would be P equals 0.10. For step 2, you need to give the symbolic form that must be true when the original claim is false. For our example, since the original claim is P equal to 0.10, it would be that P does not equal 0.10. So that'd be P does not equal, the little not equal sign, 0.10. In step 3, you need to identify the null and alternative hypotheses. Please note that the null hypothesis is always equal to. In our example, the null hypothesis is that inaccurate online orders equal to 10% or h sub 0 is P equals 0.10. An alternative hypothesis is that inaccurate online orders do not equal 10% or h sub 1. P does not equal 0.10. Continuing on with step 3, the alternative hypothesis can be greater than, less than, or not equal to. Examples would be, for proportions, h1 colon p greater than 0.05, h1 colon p less than 0.05, and h1 colon p not equal to 0.05. For means, it'd be h1 colon mu greater than 80, h1 mu less than 80, and h1 colon mu not equal to 80. And for standard deviation, it would be h1 colon sigma greater than 12, h1 sigma less than 12, and h1 sigma not equal to 12. You need to determine which of these, proportion, mean, or standard deviation, to use based on the problem. Moving on to step 4, you would select a significance level, alpha. For us, this was stated in the problem. Use a 0.05 significance level to test the claim that 10% of online orders are inaccurate. So ours would be alpha equals 0.05. For step 5, we will need to identify the statistic relevance relevant to the test and determine its sampling distribution. So there are several different ways. There's a proportion P, which would be our parameter. With a sampling distribution of normal Z, the requirements would be NP greater than or equal to 5 and NQ greater than or equal to 5. And the test statistic would be z equals p hat minus p divided by the square root of p times q divided by n. Another parameter would be mean, mu, with a sampling distribution of t, and requirements of sigma not known and normally distributed population, or sigma not known and n greater than 30. And the test statistic would be t equals x bar minus mu divided by s divided by the square root of n. For mean mu, sampling distribution of a normal z, the requirements would be sigma known and normally distributed population, or sigma known and greater than 30. And the test statistic would be z equals x bar minus mu divided by sigma divided by the square root of n. And for standard deviation sigma, or variance sigma squared, the sampling distribution would be x squared. The requirements would be strict requirement, normally distributed population, and test statistic would be x squared equals parentheses n minus 1 and parentheses s squared divided by sigma squared. In step 6, you need to find the value of the test statistic, and then find either the p-value or the critical value or values. The test statistic is computed using the approximate formula. You would input the necessary information and calculate any information that you are not given. When finding the p-value or critical value or values, you need to determine if the conditions necessitate a two-tailed, right-tailed, or left-tailed test. With a two-tailed, the critical region is in between the two extreme regions under the curve. With a left-tailed, the critical region is in the extreme left region under the curve, and for the right-tailed, the critical region is in the extreme right region under the curve. Continuing on with step 6, here are some helpful hints to determine which type is by looking at the alternative hypothesis symbol. If the symbol points to the right, which is the greater than symbol, the test is right-tailed. If the symbol points to the left, the less than symbol, the test is left-tailed. If the symbol is not equal, the test is two-tailed. Once the value of the test statistic has been found, use the standard normal distribution table to find the p-value and or the probability of results on either side of the critical value or values, and or the probability of results within the confidence interval. At this point, step 7 is different depending on which hypothesis testing method you are using. For the p-value method, you need to make a decision as follows. You would reject h sub 0 if p-value is less than or equal to alpha. You would fail to reject h sub 0 if p-value is greater than alpha. For the critical value method, also known as the traditional method, use the formula to the right to find the probabilities of the critical value and any values more extreme than the critical value.
What
That formula would be 1 minus alpha divided by 2. For example, if our significance level is 0.05, you would subtract 0.05 from 1, which would equal 0.975. Then you would go to the z table, and among the p-values, find the z-score that corresponds to 0.975. 0.975 corresponds to 1.96, which would be the critical value. The critical region would be any values greater than 1.96 and less than negative 1.96. Then you would make a decision, and you would reject h sub 0 if the test statistic is in the critical region, or you would fail to reject h sub 0 if the test statistic is not in the critical region. For the confidence interval method, you would determine the confidence interval based on the significance level alpha and whether it is two-tailed test or a one-tailed test. For example, the confidence interval includes all of the values in between the two critical values if two-tailed. Then we would fail to reject the original claim, the null hypothesis, if it is outside the values. For step 8, we need to restate the decision in non-technical terms. For the p-value method, if the p-value is less than or equal to A alpha, or for the critical value method, if the test statistic is in the critical region, then there is sufficient evidence to warrant rejection of the claim that 10% of online orders are inaccurate. Now let's work with a problem together using the p-value method for a population proportion. A random sample of 750 births of foals, baby horses, include 420 colts, boy horses. Use a 0.01 significance level to test a claim that 50.7% of newborn foals are colts. Do the results support the belief that 50.7% of newborn foals are colts? For our example, we are going to test a claim about a population proportion using the p-value method. Our first step would be to identify the claim, which for us is that 50.7% of newborn foals are colts. Then we give that in symbolic form, which is p equals 0.507. Then for step 2, we give the symbolic form that must be true when the original claim is false, which for us would be p does not equal 0.507. Then we do step 3, which is to identify the null and alternative hypotheses. The null hypothesis for us would be H sub 0, colon, P equals 0.507. And alternative hypothesis will be H sub 1, colon, P does not equal 0.507. For step 4, we select the significance level alpha, which for us was stated in the problem. So it is alpha equals 0.01. For step 5, we will identify the test statistic for the p-value method. The formula for our test statistic, which we use because the problem involves population proportion, is equals p hat minus p divided by the square root of p times q divided by n. P hat equals the sample proportion and is calculated as x divided by n. P is the population proportion. Q equals 1 minus P, the number of successes and n equals the sample size. Our p hat will actually equal 420 divided by 750. Because remember, there was 420 colts, 750 foals total. And that will equal 0.507. 0.56. As we know, our P equals 0.7. And our Q is going to be 1 minus that. So we do 1 minus 0.507 to equal 0.493. Now our formula is going to be Z equals 0.56 minus 0.507 divided by the square root of 0.507 times 0.493 divided by 750. 0.053 divided by square root of, for our bottom, we do the top part of it first, so 0.507 times 0.493. That's going to equal, it seems like 9. Alright, so we take the 0.249951 and divide that by 750, which is 3.33268 to the negative 0.4. Then we, on our calculator, hit shift square root, and we come up with the number 0.018255629. And that will, and we move our number over. And then we will divide 0.053 divided by 0.0182555629, and that will equal 2.9032141226. And we're going to round out to 2 decimal places. So Z equals 2.90. So to find the p-value, go to the Z table, which is found in the back of your book. Find the Z score of 2.9 on the left side of the Z table. Then go to the top and find 0.00 and find where they meet. They meet at 0.9981. 0.9981 is all the area to the left of the Z score of 2.90, because the Z score table shows areas to the left. We want the area to the right. Since the Z score is positive, So we calculate 1 minus the area to the left. So for us, that'd be 1 minus 0.9981. And that will equal 1.9 to the negative 0.3. So that means we move the decimal 3 places to the left. So 1, 2, 3. So it'd be 0.0019. Since it's a two-tailed test, because of the null and alternative hypotheses being equal and not equal, multiply that by 2. So we take our 0.0019 and times that by 2, and that equals, so 0.0019 times 2 equals 3.8 to the negative 0.3. So again, we move the decimal place. Their equation is 0.0038. So our p-value equals 0.038. 0.9, and that's 640. Because the p-value of 0.038 is less than our significance level of 0.01, we reject the null hypothesis. So therefore, our conclusion is there is sufficient evidence to warrant rejection of the claim that 50.7% of newborn foals are colts. Thank you for watching my presentation, and have a magical evening or morning.